Assalamu alaikum everybody, this is Dr. Ali Mugebel. In this video we look at error control for digital satellite links. We have other videos, you can find them in the link in the description below, that relates to error control coding in general. However, in this video we continue with some of the information that are needed for digital satellite links. Some of the topics we'd like to cover is error detection and correction, channel capacity, error control coding, and also would like to look at the detection and correction, block codes, convolutional codes, turbo codes, and LDBC codes. We'll look at implementation of error detection on satellite links and concatenated codes and some examples that relate to satellites. Okay. So, error detection and correction, let's go with a quick recall or introduction of coding, and then we'll go into some of the new materials. So we have, when we say error control, we mean detection and correction at the same time. Error detection depends on the nature of the signal. So the moment you detect a signal, you detect an error, you either estimate the erroneous signal or just ignore or flag the error so that the end user will know that there is something wrong, or use automatic repeat query, ARQ systems, either automatic repeat query or also known as automatic repeat request. So, and this is why we call it ARQ. So the Q stands for query. Now the retransmission, of course, ARQ is not always used. Sometimes you have streaming, like in real-time application like TV. Then, of course, you have to do some image correlation and estimate the signal. You cannot wait, and then because of the continuous stream. Now, if you are looking at forward error correction or control, then it means we are doing error correction because we are forwarding the process to the receiver. So this also usually abbreviated as FEC. We have error detection and error correction. We have error control in general, and we have forward error control. So if we say forward error control, we mean error correction. Right. At the level of the user, we can have error correction between the two users, or it could be between the earth stations, or it could be in demand. Sometimes we turn it on, sometimes we turn it off. So all these are possible. You have one code between the end users, one code between the earth stations. So it depends on who is using that code. Also recall that when we say coding, we are not saying encryption. Okay, although sometimes there could be some overlap in the understanding, but coding here we mean against error. While encryption would like to make sure that the information is not readable or accessible by unintended users. Also, when we say coding, we are not referring to pulse coded modulation or PCM, where we shape the signal for transmission. In coding here, our objective is error control. Now, also, one of the terminology that you might see, whether in satellite communication or otherwise, is codec. Codec is a combined word. We have coder and decoder. So we just take the few letters from here and there, and then we have the word codec. Remember the word modem? We have modulate, demodulate. Similarly, we have codec here, which means the encoder and the decoder together. For a satellite application, there are some requirements. Let's go over some of these applications or requirements. When you design a system, you need to look at coding efficiency, and you need to trade off. For example, in very small aperture terminal that's used in TV, satellite TV, in VSAT, the gain for coding could be 3 dB. The gain in the carrier to noise ratio is equivalent to this gain, because of coding, is equivalent to increasing the antenna size by 41%. Imagine the dish antenna that you have at the roof could increase in size by 41% to get the same benefit, which is 3.1 dB. Of course, this is in general. We are not speaking very specific here. Coding is rarely applied to digital voice, especially if you want to have application which is quick play. You don't want to decode and encode. For financial transactions, because of the importance, we're speaking of error that must be less than 10 raised to the power minus 12. You don't want to go to your bank account and find the numbers are different because of the error in the coding. And of course, for this kind of application, you need ARQ, just to make sure that things are not messed up. Also note that as we increase the frequency, our expectation and performance would differ. So the propagation characteristics of high frequency is not the same as low frequency, so we might tolerate lower probability of error, like 10 raised to the power minus 6. Of course, the application has to be appropriate. One of the terminologies also used in satellite applications or otherwise is a protocol. The protocol defines an operation procedure in a link, whether the coding protocol used or whatever protocol is used for communication. Usually, the encoding is left to the user. So there could be coding at the workstation, at the Earth station and satellite link, but also there must be some level of coding that's used for the user or left for the user to guarantee a certain probability of error for a given time or percentage of the time. And this includes military use. For example, the military application satellite would use their own code to guarantee the accuracy. This is not for encryption, just to guarantee the accuracy for a given time. And also, for example, the digital broadcast satellite TV use user-defined code. You can have your own, you can have your own code with the channel that transmits. So these are some of the important information I'd like to recall before we go into some technical stuff. All right, here is Dr. Ali Mugebel, and we speak about channel capacity. I have other videos before I start about channel capacity, and you might visit the following link or search for a capacity of a Gaussian channel if you want more theoretical perspective. So here we just touch on the topic from satellite point of view and satellite engineering point of view. The channel capacity measured in bits per second is an upper limit on the information capacity of the channel introduced by Shannon. It's usually known as channel capacity theorem or third law of Shannon or Shannon-Hartley law. So it says there is an upper limit for what you can transmit in bits per second for a given channel. If we assume that the channel is a wide Gaussian noise channel, usually we do that for simplicity, we'll find that the capacity, which is H, is this, which means the maximum bit per second that you can transmit, is given by the following equation. So it relates to the bandwidth. So H is the capacity, which is of course 1 over the bit duration. This is the rate, maximum rate. So TB is the minimum duration per bit, if you like. So it's going to be the inverse. Rate and capacity are the same, so the duration will be the inverse. All right, so we mentioned that it's controlled by the bandwidth in hertz. The amount of power that's received in watts, this is the received power in watts, how much power we received at the receiver side. Of course, it should be proportional. And also, not the bandwidth appears here, okay, appears in both locations. And of course, it's inversely related to the noise. So N naught is the single-sided noise power spectral density in watts per hertz. Fantastic. So we can also write this equation in different formats. Remember that EB is the energy in the bit, and energy and power is related by time. So we can say that the energy is the power times the duration. So I can say that EB is equal to P times TB. We also mentioned that TB and H are inverse, so we can also say P over H. So I'm trying to fit the energy here, so we're trying to find some relations here. We can also say that if you divide by N naught, I will get, of course, P divided by H divided by N naught. Fantastic. Now, if you look at spectral efficiency, this is it's measured not in bits per second, it's measured as bits per second per hertz. How much rate you have for every bandwidth given, for every hertz given. So this is bits per second, and this is signal or spectral efficiency. It's not the capacity, it's spectral efficiency. So we can take H divided by B at both sides. This is going to cancel out. Now what's inside, you can see that these are equivalent. Okay, so these are equivalent. I can replace, of course, P here with H times AB. So from here, the denominator is the same. The only thing is P equal to H times AB. Okay, so you can see the same equation. Just it tells you that given the bandwidth, given the power, given the noise, then no matter what you do, there is a maximum bit rate that you can tolerate or you deal with. Of course, one other format to write this equation, of course, if you take 2 to the side, so you have 2 raised to the power h over b, and then you subtract 1. So whether seeing this or that, it's just a relation in a logarithmic scale, or and this is in the power format. It's just the same equation. Okay, so this is the channel capacity and the spectral efficiency. Now looking at the channel bound, it says that the capacity equals to the bandwidth times log base 2 of 1 plus s over n. And this is another way of writing it. So if you just multiply here by n, divide by n, e, multiply by e, divide by r, multiplied by r, so you just have nothing extra here. Inside, similarly, we can write in terms of signal to noise ratio, if you like, or any of the other formats. So the signal in green equal to the rate, signal equal to the rate times EB. And also the signal power equal to rate times EB, or if you like, E divided by time. And the noise, of course, equal to N naught times B. This is the noise spectral density. So if you multiply the bandwidth, you get the noise power. So we can use S or P alternatively. Alright, so cool. Here we have the signal to noise ratio is replaced by this, as we mentioned. If you now take the limit of the capacity as the bandwidth increase, so no matter what the bandwidth is, okay, taking the mathematical limit, remember that the bandwidth appear here and appear here. So taking that limit, I'll find out that the capacity equal to 1.443 times RB. So the limit of the inside term, remember this is x here, okay, and this is 1 over x. So this is like log 2 of x over x, which is equal to, related to log 2, so we can find it to be 1.44, and this is equal to RB multiplied by this terminology. So the capacity has to be less than this, as in goes to infinity. Remember that the rate that you transmit must be less than the maximum, must be less than the capacity. So RB we can say equal, less than or equal to the following. If you divide both sides by RB, this tells you that EB over N naught must be greater than or equal to 1 over 0.443, which is equal to minus 1.6 in dB. And this is why we're saying that no matter how much is the bandwidth, all right, the minimum that you can communicate with to make sure that the rate is less than the capacity is, or to have a positive capacity, is that EB over N naught should be greater than or equal to minus 1. So this is the minimum signal in EB over N naught that we can tolerate in communication. Required channel quality for error-free communication is that we must have EB over N naught to be greater than or equal to minus 1.6 dB. So if this is the case, we can have some capacity. But of course, we are doing much worse than this. We are not up to this limit. We cannot communicate at this limit currently. We are getting closer, so we need to find a solution. And the solution would be through the utilization of coding. In these diagrams, we show the relation between, we have two scenarios. We have the power limited scenario and the bandwidth limited scenario. In the power limited scenario application where we have problem with the power, so in fact, if you look at this axis, and if you look at that axis here we have the E over B, we have small power. However, in this side we have the larger power. If you want to connect the two curves, it's possible, but I just want you to know that the y-axis determines the power. So in this part we are in the low power side, power limited application, while the x-axis represent the bandwidth or the capacity relative to the bandwidth. So if you are going in this side, okay, the capacity relative to the bandwidth is high. So this is bandwidth limited. Okay, so because the numbers here are high, comparing the capacity with B, we're taking the log scale, of course. Fantastic. So this shows you that here is the relation, okay, and we can see that the minimum power for communication, the minimum AB over a node, is minus 1.6. So there is no curve here. So this is the relation between H over B, the spectral efficiency, and the energy. As you go low on power, the spectral efficiency decreases, it goes to the side. As you increase the power, the spectral efficiency increases. So as we go up, we can see that the spectral efficiency increases. This is called the power limited case, and this is the bandwidth limited case. Okay, so you cannot exceed this relation. So here we have H over B is small, less than 1, or H is less than B. This we call it the power limited. We have bandwidth. The bandwidth is greater than the capacity, the capacity. While here we have to look at the case where we have bandwidth limited. Okay, so you know here that some examples for QPSK with error of 10 raised to the power minus 6, the required EB over N naught is 10.7 dB. Okay, and we are transmitting 2 bits per second per hertz. So we are here. Okay, and to get that much of error, you need 10.7. So we are much more than the capacity. So if you look at 2.7, that's here, you have very small energy. So this is showing you the limit. For theoretically, what you need is just 1.77 dB. So if you look at here, you should have small, because if you take H over B for this case, it's going to be 2, log base 2 is 1, so we're speaking about 1.77 dB. However, what we are doing currently is 10.6 dB. Similarly, the case for the 256 QAM, the required EB over node is 2.13 dB, or carrier to noise ratio is going to be 30.3. Of course, there is a difference between these two, because one for the symbol and one for the bit. So we have about 2, we have about 9 dB difference. Okay, because we have 8 bits per second. Theoretically, every multiple of 2 will require 3 dB. So we have theoretically what we need is just 15 dB. If you look at 8 bits per second, then you get here 3. You'll find that what you require is just 15 dB. So you can see that we are far away from these limits. We need coding to get closer to the bound. So we'll be speaking about coding as we go on, because we want to get to channel limit. Here's another example of operation point example. These are the Shannon capacity. Here we are plotting differently. Here we have the signal energy in dB, and here is the power spectral efficiency. This is a comparison between different modulation schemes on the bandwidth efficiency for a probability of error that we chose to be 10 raised to the power minus 5. Just a chosen number, because we cannot compare at 0 dB. We cannot compare with no errors. So you can see here that these are the different techniques. For example, if you look at the PSK, or differential PSK, you'll find out that as we increase the constellation, from 2 to 4 to 8 to 16. Okay, we have bandwidth, we have spectral efficiency increases because we are sending 2 bits here, 3 bits, 4 bits per transmission. But of course, to get the same error, you need to increase the power. Fantastic. Now, some other techniques, you notice that you're going in the other direction. For example, what's this triangle frequency shift keying? Of course, as you increase the possible number of frequencies, what happens is the efficiency decreases because you are covering more bandwidth. Remember, in FSK, every time we add the concentration point, we are decreasing, we take more bandwidth. But of course, the power requirement will become less. So, because we are paying the price in Spectrum. So please freeze the video and look at this diagram carefully. You need to be able to relate the modulation with the diagram. So this is this is the channel limit. We cannot have any possible communication here. So if somebody says, can we have energy of this value and then power spectral efficiency of 4? The answer is no. Why? Because we are exceeding the channel capacity bound. Okay? And remember here that there should be nothing, no communication below minus 1.6. So the bound stops here. So there is a vertical line here. Here's another example of what we do with modulation schemes. As we increase, this is now we're plotting the approach error versus EB over a node. Okay, we can see that as we increase the constellation, if we keep the power constant, it means the error would increase. So we have to pay the price in terms of power. Here's of course the channel limit, which means that we cannot go below this and get some meaningful communication. Okay. So this is a very now let's conclude this part with a quick quiz. First question. In channel coding theorem, channel capacity decides the space allowed rate at which error-free transmission is possible. The missing word is minimum, maximum, standard, constant. Mark your answer in the comment section. For the second question, on which factor or factors do the channel capacity depends in communication systems? Is it the signal power, bandwidth, noise power, or all of the above? The third and last question is, if the channel is band limited to 6 kHz and signal to noise ratio is 16, what would be the capacity of the channel? So make your choice, take your time to do the calculation, and mark your answers 1, 2, 3 in the comment section. Fantastic. These are simple questions, but the objective is to make sure that the basics are gained. Thank you for being good listeners, and we'll continue with coding. Remember, we have motivated our topic of coding using the channel capacity. So see you then. Thank you very much.